group did a hydrographic survey and scanning of a bridge. It is made up of Devin Anderson, Daniel Byer, David Hall, and me, Andre Duclay. Next slide. An overview of what we're going to be going over during this presentation. We'll begin with an introduction. We will go over the objectives that we planned out, a description of our site, the process of our data collection, our data processing, the tasks that we completed, what went wrong, and the acknowledgements. Next slide. Our site description. It was a bridge in Paris, Michigan. It is Hoover Road. It is approximately 250 feet in length. It spans over the Muskegon River, and it's a public road. Next slide.
Yep.
These two pictures here were created using Trimble RealWorks and Trimble Business Center. These pictures were made using the laser scan data of multiple scans, I believe over 6 or 7, to have full coverage of the sides and the bottom and top of the bridge and the surrounding areas. Next slide, please. For our original objective, they were to establish and set control around the bridge, which we were able to complete. The laser scan of the bridge and all the surface areas that were above the water, which we were also able to complete. And then the other objectives were the hydrographic survey of underwater surfaces, which was left incomplete, but we did attempt. And then there was the joint 3D model of the bridge and the underwater surfaces, which was also left incomplete. Next slide, please. Cost estimate. For the costs, we had the scanner fee for $5,000, the hydro fee for $3,000, a professional surveyor fee for $500, labor fees, $1,440. Traveling cost was estimated to be $130. A processing fee of $650, and a miscellaneous costs of up to $1,000, totaling to $11,720 total for estimated budget. If this were to be a real survey group and we were to have to pay for our own equipment, I believe that we were very well within our budget. So yeah, next slide, please. Time allocation. For establishing control, we had 1 or 2 trips planned, and it took 2 trips to establish control. We first went out there to find what we wanted, where we wanted to place the points, and then to actually place the points. Scanning, we originally only had 3 trips planned, but because we were trying to learn the equipment and use it better and more efficiently, it actually took 5 trips to complete. For hydrographic survey, we only planned for 1 trip using the hydrone, but that initial trip was unsuccessful due to multiple complications with the equipment and just unfortunate outcomes. And this was left incomplete due to the COVID-19 outbreak, and the 3D model could not be completed because we did not have access to the software or the underwater data. So next slide, please.
The first portion of the whole Capstone project was the scanning. we did a total of 10 scans. We used the Trimble SX10, a tool that helped us along the doing the project was a polygon tool. And the target that we used was the Trimble multi-track target. Um, and we got it to be within a thousandth of a foot. The materials or the instruments was the Trimble SX10. The target that we used was the multi-track target. For the materials that we used for the different control points was the keel, the hammer for the PK nails, and the hubs. About the Trimble SX10 was it's a digital scanner and capable of shooting 20,000. Can you go back? 26,000 and 26,000 and 600 points per second. It can shoot as
Devon,
far.
Devon, wait a minute. David and everybody else, can you mute yourself because let only him speak. And when it's your turn, you can unmute yourself. Otherwise, there is a lot of background noise that is coming in. You can carry on.
All right, so the Trimble SX10, it's a digital scanner with a total station. It's capable of shooting points as fast as 26,600 points per second, and it can shoot points as far as 600 meters. And when you shoot a point 100 meters at distance, the spot size is 14 millimeters, and the angular accuracy is within like 1 second. The target we used was a multi-track target. It uses Trimble active tracking technology, which enables you to use a Trimble SX10, and it tracks it as you're going along like bushes. It's able to track you as you're moving. The accuracy for that one is within like 5 seconds. It can be tracked as far as 800 meters, and it has 8 different channels, which is helpful when you have like different instruments when you're trying to like use different instruments on the same target. Yeah, the next one. Okay, on the first day we set up control. We used 10 control points. I think we had like 2 or 3 on top, and then like 7 were on the bottom. We had to use a local coordinate system because the first core station could not reach that far, so we had to use the first point as 5,000, 5,000. We had 10 scans on the top and the bottom of the bridge. On the first day, we did use the dome tool, but we decided that we got too much data, and it took like over almost an hour. So then we learned about the polygon tool, which we are able to like select the area of focus that we want to scan, which was very efficient. We use Trimble Business Center to process the data. Next one. The scanning for the control points, we had again 2 points, top and bottom. We used the hub and nail only on the first point when we had to set it in the ground when the ground was wet, because if you put like a nail in, it's very easily to move. So we use a hammer to hammer in the hub and nail. PK nails we used in like the pavement under the bridge, and only time when we used a keel was on the deck of the bridge, and which was helpful because we couldn't use like a nail in a concrete. The data processing, we use Trimble Business Center. Okay, we use a point cloud for like the model, but then we use images to color the points, so like it overlays on the points, and then we plan to make a surface of the water bottom when we use a hydrographic survey if we completed it. And then we use a point cloud to use for the 3D printing, but we were not able to create it because of the whole like virus situation.
So the second phase of our project was the hydrographic survey of the riverbed surrounding the bridge. To accomplish this, we plan to use a hydrone. The hydrone was outfitted with a single beam sonar scanner, and both of those were provided to us by Mark Tenhove from Seiler Geospatial. Initially, we wanted to use a multi-beam scanner, but we couldn't get access to that, so we made do with a single beam scanner. As the hydrone was out in the water, it was being tracked by a Trimble S5 total station set up on the bank of the river, and a prism was mounted on the hydrone itself. Because we were having connectivity issues with the controller for the hydrone and the hydrone itself, we tied a rope around it so that it didn't drift away, and someone stood on top of the bridge with the rope just in case the controller disconnected. We set up the hydrone to take shots every 3 seconds. We could have had it do more, but we decided that that was good for what we needed. So here's the hydrone. It was manufactured by Seafloor Systems. It's laid out. It's got 2 floating sections connected by an aluminum frame. Each section has its own propeller, which are each controlled independently by the controller, which is how you steer it. In the center there, you see the rod. At the top is the prism that was used to track the hydrone. The bottom is the echo sounder unit, which sends out the sounds and they come back. And in the middle is like the processing unit. Here's a picture of the inside of the hydrone. There's the battery. Here's the on-off switch. You can independently turn each motor on and off for each pontoon. To process the hydrographic data, we were going to use Trimble RealWorks to create a digital elevation model from the sonar data we collected. And then we were going to merge that model with our bridge scan to create one uniform model. Trimble Business Center, use that to process the 3D scanner data. I feel like I'm missing a slide here. Maybe not. Okay, so after we created the model in Trimble Business Center and Trimble RealWorks, we were going to make a 3D print of the whole model. To create the model to print from the point clouds that we had, we were going to use MeshLab. It's a free software used to create 3D printable surfaces from point cloud data. Our first attempt at creating a 3D printable model, we used the Poisson filter. Initially that failed, and we were unable to make another attempt due to the COVID-19 virus. If we were able to create a 3D printable model, we were going to use the 3D printers located in the plastics building. Yeah. Okay, Dave? Uh-oh. Did I?
Okay, so completed tasks.
Did you all hear that?
Well, yeah, I just had to remember to unmute my.
No,
What's
no
that? So, complete task. What we've gotten done so far, we managed to set up control, and we're able to get the bridge scanned from 360 degrees of different angles to get above and below the bridge from different directions. We attempted a hydrographic survey, but that was unsuccessful, and due to the shutdown, we were unable to go back out and do another survey. So unsuccessful tasks, as already mentioned, we were not able to do the hydrographic survey. Also, we wanted to create a 3D model and then print it with a 3D printer, and we are also not able to access the facilities we needed for that due to the shutdown. Conflicts. Some of the conflicts we had to deal with was, one of them, we set the instrument up at different heights, and that caused our measurements to be out of sync with each other, and we didn't know how to work the equipment to adjust it so that they meshed up. And that created a lot of time loss right there. And then understanding basically how to use the equipment, like how to set the projects up when we got out to the sites, that took a lot of extra time because we're just learning the equipment at the time. Another thing that we had a problem with was the SX10 controller battery had a short lifespan due to we think it's probably due to the cold weather, but we're not 100% sure on that. Also, we had a problem with the Hydrone. Its controller was not responding to the drone, and so we kept losing signal. So we attempted to control the drone with a rope attached to it, but that ended up tangling up in the propellers and making it so we lost control of it, and it ended up being caught in some brush that we had to have friends come out after that and come rescue our the drone from out in the pile of brush out in the middle of the river. COVID-19 was a serious problem for our group. We had a lot of things that we wanted to still do, all our finish-up work, and we suddenly had to figure out how we could work to get around different things. We did a lot of over the web sharing, but there's limitations when you don't have facilities and labs where you can go to do use software. So yeah, we were unable to get the 3D model created and printed because of that. Acknowledgements. For our project, we were supplied with equipment through Ferris State University and Seiler Geospatial. They provided us with SX10 scanner and total station. Seiler Geospatial also provided us with a hydrone that we used when we tried to do the hydrographic survey. Individual acknowledgements. Mark Tenhove, geospatial survey salesman for Seiler, he helped, he provided us with the hydrone, and he also came out and assisted us in the operation of it. He also provided us access to Trimble Rail Works and Trimble Business Center. Tim Dyer, he had a kayak, so when he heard that our drone had got stuck, he came out with the kayak and he rescued the hydrone. John Feisey also came out and assisted in the rescue operation of the hydrone. And that's our project. Thank you all.